Good morning, students. Good morning, everyone. Let's begin today's session. So we were discussing doubts from H.C. Verma last time from Newton's laws of motion. Today we will start with the concepts of friction. And basically, friction is the next chapter as far as your sequence of chapters is concerned, but it is a continuation of Newton's laws of motion. Yeah, we discussed about spring force also. So friction is going to be a continuation of Newton's laws of motion, where we will continue discussing about the free body diagram method of applying Newton's second law, but just in situations where in addition there is also the frictional force. Okay, so after we finish the concepts of frictional force, we will come back to the questions from your module exercise, etc., which will be both inclusive of Newton's laws concepts as well as the additional concepts of friction that we are discussing today. So let's start with the theory discussion and understanding of friction. So as I said, this is on your sequence of topics. This is like a next topic, but actually it is more like a continuation of Newton's laws. Okay. Major test 4, I will tell you the syllabus better. In major test 4, there will be entire Newton's laws of motion, but friction will not really be coming in that. Okay, only the very basic thing about friction will be coming. But anyhow, we will discuss before that. Okay, because we have a couple of weekends before that, so we will have completed the portion for your major test 4 well before 4th of January. Okay. Main thing is you focus on completing the H.C. Verma exercise of Newton's laws of motion and then get started with the module exercise. Okay, then you should be in a good position for this. Okay. We'll also do some revision questions before the test, so don't worry, Tej, you'll be prepared for that. Okay. Right. So let's start with the discussion about friction. So I think all of us know some common everyday meaning of the term friction. Friction is the type of force that acts whenever there are whenever there is rough surface with slipping against another rough surface. So for example, on a concrete floor, if you're trying to push a block which is made of wood or a block which is made of stone or something like that, and the surface is not polished, or even if it is polished, there will be some amount of friction, but the amount of friction will become less. So generally speaking, the smoother the surfaces of contact are, the less amount of friction, but there is always some kind of resistive force when we try to slide an object against some surface, and that kind of resistive force or that kind of frictional force is what we are talking about. Yeah, Rachit, we have discussed about spring force. We have completed spring force last time. There's nothing else about spring force. Okay, the formula of spring force we've discussed, and you can work out the questions from HCV about it. Okay, we will discuss the questions when we finish friction. Okay, um, let's please start with friction. I'm getting interrupted too many times. Okay, let's yeah. So let's understand the definition of friction. So friction is a contact force like normal reaction, but the difference is normal reaction acts perpendicular to the plane of contact or normal to the plane of contact, whereas friction acts parallel to the plane of contact, that is along the plane of contact, but in such a way that it is opposing slipping. So when does friction act? Whenever two surfaces are either slipping with respect to each other or they have a tendency to slip with respect to each other. Okay? And in that case, there is a tangential or a parallel kind of force that acts, which is against the slipping, which is against the tendency to slip, and that is called friction. So friction is a type of contact force that acts between two surfaces, especially if they are rough surfaces, in contact. Okay, when they are either slipping, okay, with respect to each other, slipping or sliding with respect to each other, okay, or have a tendency to slip. They have a tendency to slip, okay, due to external force. Okay, so friction is the contact force that acts tangentially. So tangentially means along the surface, okay, along the surface of contact, okay, such that it opposes slipping. The direction of friction is always such that it opposes slipping. Okay. So just make a note of this definition first, then we will understand this definition better with some examples with diagrams and things. Yeah, I'll explain, Kunal. Just give me a moment. Tangential का मतलब क्या होता है? Just like in coordinate geometry, ना, the tangent at any point is, along the surface or along the curve. So in this case, we're talking about a surface instead of a curve. It's a three-dimensional situation. So, so for example, if you are sliding a block on a rough floor, friction का direction क्या होगा? It will be along the surface, ना? It will be along the floor. It will not be perpendicular to the floor. It will not be vertical. It will be horizontal along the surface. Okay, the direction of frictional force. So that is why it is called the tangential direction. Okay. So let's take a situation to understand this. Okay. So next we have this. Suppose that we have kept a block on an object on a rough surface. Like I mentioned earlier, you can have, for example, a rough concrete surface, and on that surface you have placed a block made of whatever, let's say a wooden block. So this is a rough surface. Okay. And block of mass m is placed at rest initially. Now we are trying to make it slide along with the application of some force. But in this case, we will see that definitely the acceleration of the block will not be F by m the moment we apply the force. In fact, the block may not even slide. It may even so happen that we are applying the force, but at the same time, the block is not sliding. So what we'll observe is that, okay, if a comparatively low amount of force is applied, comparatively small force, small magnitude force, is applied, okay, the block may not even move. May not even move. So why does that happen? That happens due to the friction applied by the surface. Okay, by the surface, in this case it's a horizontal floor on the block, such that it opposes the tendency to slip. And the moment we have applied a force, there's a tendency to slip, but that tendency is opposed by friction. So when we think of the free body diagram, this becomes even more evident how this is happening. When we think of the free body diagram, we'll understand that the forces, so obviously there's the external force F we are trying to push the block with. And obviously there are the standard forces of gravitational force or weight of the block and the normal reaction that the ground is applying. But in addition now, something else is happening. Otherwise the block would have developed a horizontal acceleration. Had this been a smooth surface, we would have observed that it starts accelerating, but we are seeing the acceleration is zero. The block remains stationary. That means there is another force that is applying. And definitely there's no other external agent who's pushing from the other side. So it's happening at the surface of contact. The floor is applying, the rough surface is applying a force like this, and this is opposing. Okay, so this is in fact an example of what we call static friction. This type of friction is in fact called static friction, and we'll discuss more in detail about static friction next. So you can see here that free body diagram wise what is happening. Normal reaction is Yeah, so we got disconnected. We'll just continue. Yeah, so coming back to this free body diagram, people, you can see that in this case, why the body is not accelerating, because the static friction is balancing the external force that we are applying. So basically, we're not able to overcome the friction in the surface, and the acceleration is remaining zero. Yeah, write it down, please. No problem. No, the friction will act the moment we apply the external force, Diti, and therefore it will not allow the block to move. Okay, the type of friction that acts for a moving block, that's a different friction. We'll come to that. That is called kinetic friction. But it's not that we apply the force, the block starts moving, and then friction acts. It's like we apply the force in this case, and we are seeing the block is not able to move. Why? Because we are not able to overcome the friction. Okay, think of a situation where you have a very heavy object on the ground. You're trying to push it, but you're not able to move it. Why that is happening? Okay, that is happening because of the friction on the ground. No? Otherwise, if there was no friction and it did not act when you were pushing it, then the block should have started sliding, no? And friction would act after it started sliding. But you know from your everyday experience, it doesn't happen that way. You know. Now there are a lot of factors we have to understand before we get the full picture over here. But this is just a from a point of view of observation. Okay. So we observe a situation like this, that we are applying a force which is comparatively less in magnitude, and therefore the block is not moving. What is the conclusion that we can come to from that observation? The conclusion is that the friction is balancing the external force. The moment we are applying this horizontal external force, the friction starts acting from the ground, and therefore the block is not moving and is balancing it. So it is called static friction. This type of friction is called static friction. Hence the subscript S over here. So generally we use the symbol small f for friction in a free body diagram, and small f with S written on the side or as a subscript means that it is static friction. Okay, so for example, in this case, suppose the mass of the block is 10 kg. Okay, so the weight is approximately 100 newtons. Normal reaction is 100 newtons. What we are observing, that if the force we are applying is suppose 20 newtons, and we are observing that the acceleration of the block is zero, it remains at rest. Okay, because comparatively the force is less, it's only 20 newtons, and the weight of the block is as much as 100 newtons. So what we are observing from this is that static friction equal to 20 newtons is acting on it. That is the conclusion from this. And the magnitude of static friction is acting is equal to the external force of 20 newtons. And you can see how the static friction is acting. It is acting tangentially such that it opposes the tendency to slip. It acts tangentially. So tangential का मतलब क्या है? Along the surface. At the surface of contact, it is acting along the surface. Whereas normal means perpendicular to the surface. Okay. Now supposing in the same example, next, suppose we increase the magnitude of F from 20 newtons, this case, to let's say 60 newtons. Okay. And observe the block has started to slide. It has started to slip at an acceleration of 4 meters per second square. So what we are observing, or let us say the acceleration is not 4, but the acceleration is 2 meters per second square. So what we are observing is that the acceleration is less than F by m, because 60 newtons on a mass of 10 kg, had the acceleration been F by m, it should have been 6 meters per second square. But the acceleration is less than 6 meters per second square. It's only 2 meters per second square. So why this is happening? Again, because friction is acting, but this time a different type of friction is acting. And that type of friction is called kinetic friction. So through this example, we will understand that there are two types of friction that can act: kinetic friction and static friction. So in this example, what is happening now is that we are applying the same amount of, the block has the same mass, is lying on the same surface, but the magnitude of the force we are applying it, we have increased that from 20 newtons in the previous example to 60 newtons now. And as a result of that, what is happening is, because we've increased the force considerably, now friction is not able to prevent the slipping. It is not able to keep the block at rest. But at the same time, it's still doing something. It's not altogether absent, because the acceleration of the block that we are observing now, we are applying a force of 60 newtons, but the acceleration we are observing is only 2 meters per second square on the same rough surface. Okay, so now for us the conclusion becomes that there is friction acting, but that friction is doing a different job compared to earlier. This friction acting now is doing the job of reducing the amount of acceleration. It's not able to prevent slipping, but it is opposing slipping nonetheless. Okay, so this is the amount of, see, now this force of 60 newtons is creating an acceleration of only 2 meters per second square. So that means there is friction acting, but that friction is doing something different now. It is not able to prevent slipping. It is opposing slipping. So this is called kinetic friction. So here what is happening is that this is our first equation, but F minus kinetic friction is equal to ma. So this kinetic friction acts tangentially, okay, opposing the slipping. It is not preventing the slipping, but it is opposing it. Okay, and therefore we can see from here that 60 minus kinetic friction is 10 into 2. So the amount of kinetic friction acting, the magnitude of kinetic friction is 40 newtons. So it is less than the external force. Okay. So this is the observation over here from this current situation, okay, that when we applied the force of only 20 newtons, it was not able to overcome the friction. No. The ground was able to balance the external force by applying a static friction of 20 newtons, and the block was at rest. But when we increase the force to 60 newtons, what we are observing, we don't have enough friction available to us to prevent the slipping. So the block starts slipping. Okay. So kinetic friction starts acting on it. And kinetic friction is the type of friction that acts between two surfaces which are slipping with respect to each other. So the observation is this: कि मैंने force 60 newtons लगाया, but the acceleration is 2 meters per second square. So what is the conclusion from the observation? That there must be something acting in the opposite direction, which is less than 60 newtons. It's not equal to 60 newtons, because then the acceleration would have been 0. Okay. So the conclusion is that type of friction acting now is kinetic friction, because it is the friction acting between the block and the surface when the block is actually sliding on the surface. It is not at rest. Whereas in the previous example, the block was at rest with respect to the surface and the friction acting was balancing capital F of 20 newtons. So that type of friction is called static friction, when it acts between two surfaces at rest and prevents the tendency of slipping. Whereas when the two surfaces are already slipping with respect to each other, the type of friction that acts to try and oppose the slipping, instead of preventing the slipping, it is opposing the slipping. Friction नहीं होता यहाँ पे, so the slipping would have happened at an acceleration of 6, but because of friction the amount of acceleration is reduced to 2 meters per second square. So that type of friction which opposes slipping, that is called the kinetic friction, whereas the type of friction that prevents slipping altogether, it does not allow slipping to happen, that is called static friction. That is the difference between static and kinetic friction. So just make a note of this example in detail. Harshal, is the point clear about the difference between static and kinetic friction? Yes, in this particular case, that is what is happening, Rachit. Okay. As I said, we will discuss more about the properties of static and kinetic friction. Just note down this example so far. Not necessarily, Diti. Okay, we'll discuss about the magnitude. It is, the example is just in context of the situation we've discussed that. Okay. Yes, that's correct, Harshit. Okay, so let's come back to this and understand that there are two types of friction. static friction, which we generally denote with this symbol, kinetic friction, Fk. Okay. So if there is a tendency to slip due to external forces, okay, but friction acts such that it prevents slipping altogether. Okay. Then the type of friction is called static friction. Okay. Whereas if friction is acting in a situation such that if friction is acting at a surface of contact where the slipping is taking place, okay, where slipping is already taking place, then it is called kinetic friction. Okay, so kinetic friction will also act such that it opposes the slipping, but it is not able to prevent the slipping altogether. That is the difference. Okay. Now, how much is the static friction? How much is the kinetic friction? We'll come to that. We'll discuss about that. Okay. Okay, so next up, let's understand more about the properties of static and kinetic friction by further exploring similar situation that we had seen earlier, but with more detail. Okay, so this same situation where this block of mass m lies on this rough surface. Okay. Now, initially it is at rest. Once again, okay. But this time we start applying a force which is not altogether suddenly a force of 60 newtons or suddenly a force of 20 newtons. Rather, it is a force which we are very slowly increasing. So F is a horizontal force, okay, which is gradually increasing with time. Okay. So such that we are controlling the force, suppose, in such a way that we are increasing the force with respect to time, like this. Suppose we are very slowly increasing the force in magnitude, okay, with respect to time, like this. Okay. Now we'll observe something very interesting, that logically, if you think what is likely to happen in this experiment, given that it's a rough surface, you will see that the block will not accelerate for some time. But the moment the force crosses a certain amount of magnitude at some time t naught, let's say, the moment the force crosses a certain value, let's say f naught, the block will start to slide. So the observation here will be something like this. The observation will be, if we do this experiment, actually, the observation will be something like this, that initially the block does not move, okay, until the force exceeds a certain value, let's say f naught. Okay, and thereafter, as f increases further with time, okay, you'll observe that the acceleration of the block increases. Okay, so what we'll observe from this is, now if we simultaneously plot the acceleration versus time graph for the block, okay, so just think of this as if we are doing an experiment, okay, and we are plotting our results of the experiment on a graph paper. So the second graph that we are plotting is the acceleration versus time. That will come out to be like this. The acceleration will be 0 till your force reaches a certain value. That is at time t naught, it reaches that value. And thereafter, the acceleration will increase with time. Okay. And when the force exceeds f naught, there will be a sudden jump in acceleration. It will not start from 0. So I'll explain that point also. Okay. So first make this graph and write down this result, then we'll understand the interpretation of the result. Yes, there is a sudden acceleration when the force exceeds f naught. I will explain why that happens. नहीं नहीं स्मृति बेटा, this is not angle of inclination. ये time का graph है ना. Force is acting horizontally only बेटा. We are not applying the force at some angle. The force is acting horizontally only. This is force versus time. So it's showing the magnitude of the force is increasing with time. Okay. Acceleration remains 0 up to this time t naught, and then after that the acceleration also starts increasing with time. Okay, so let us understand the interpretation of this. So how do we interpret this result? So what is happening for time 0 to t naught? Okay, this much time, the amount of external force we are applying is less than equal to F naught, and the acceleration of the block is 0. So that means what is happening? We are applying a force greater than 0 but less than equal to F naught. So that means external force is applied such that the block has a tendency to slip. Okay, but static friction is preventing slipping. Okay, so in that situation, the free body diagram is looking like this. Okay. The acceleration of the block is 0. Okay, the block is at rest, it is not slipping. Okay, so that means F is equal to static friction, but up to a value of F equal to F naught. Okay, that means, okay, but at t greater than t naught, what is happening? Our external force is becoming greater than F naught. So the moment that happens, static friction is unable to prevent slipping. Okay, so that means there is a certain maximum friction that is available to us. We don't have infinite friction available for any given surface. There's only a certain limit up to which static friction can do its job of preventing slipping. The moment the external force exceeds that situation, static friction cannot do its job. It gives way and the slipping starts. Okay, so just write down this first part of the interpretation, then we'll understand about the next thing, and we'll see what that limit depends on. Okay, so the moment we understand this, that the graph of acceleration versus force or acceleration versus time is showing this, that when the force exceeds, so in this part of the graph, what is happening? Static friction is balancing F up to T equal to T naught. That means up to F equal to F naught. But now the moment this thing is happening, T greater than T naught, F has become greater than F naught. Static friction is unable to prevent slipping. Okay. So that means there's a limit up to which static friction can do its job. No, we will come to that. Yes, F naught is not static or kinetic friction. Okay, F naught is the external forces limit. So we'll come to that. Okay. So further now we can see that the observation is that therefore static friction, okay, it adjusts itself according to the external force F, but up to a maximum limit. Okay, so for example, okay, for example, if F is equal to 0.2 F naught, okay, then acceleration of the block will be 0 and static friction will be equal to 0.2 F naught. If F is increased to 0.5 F naught, then again acceleration is 0 and static friction is equal to 0.5 F naught. Okay. If F is increased to 0.98 F naught, very close to F naught, even then acceleration will be 0 and static friction is equal to 0.98 F naught. But the moment F becomes greater than F naught, okay, even slightly greater, 0.0001% greater than F naught, what happens? Static friction cannot adjust to balance F and the body starts to slip. Okay. And slipping occurs. Okay. So it cannot adjust and slipping occurs. So that means static friction has an upper limit or a maximum limit. In this case of F naught. That is the first conclusion we can come to here. Yeah, Newton's law is third law is there, beta, but here we are discussing about the free body diagram of the block. Now, it's not about you're applying the external force on this block. Okay, so what is happening? Whoever's the person who is applying the external force, they will experience an equal and opposite reaction. So that is Newton's third law. Okay, the ground is applying a friction on the block like this. So the surface itself will experience a friction in this sort of direction. This is your action reaction pair. Action reaction pair can never act on the same object. Understood, Diti? So that way, if you look at everything involved over here, it's a very interesting situation. If this person is pushing the block with some force F, pushing with F, Okay. Then the block's free body diagram will have F and friction. Okay. The person's own free body diagram will have a backward force F acting on him, equal and opposite. Okay. And if he is not slipping on the floor, that means there's friction on him also acting forward. So that's preventing him from slipping. Okay. So that's why if you wear slippery shoes and you're trying to push something very heavy like a car or a bus or something, you can even slip because of that pushing force. If the friction is not enough, then the reaction force that is acting on your body will cause your feet to slip against the floor. Okay. Or imagine this, that you're on roller skates and you push against a wall. What happens? You get a backward momentum, no? Because that's because of the reaction force that the wall applies on you. Okay. But in this particular case, we are not concerned with all this. We are only concerned with the block's free body diagram. We are concerned with what's happening to the block because we are trying to study the frictional force that is acting on the block. So that's why we have not talked about all this right now. We only talked about what's happening to the block. Yeah, good. Okay. Right. So now scroll up a bit. Okay. All right. So just analyze this whole thing once more. Then we will come back to the discussion about limiting value of static friction or upper limit of static friction. And also we'll discuss about kinetic friction. Yeah, I'll scroll up to the diagram also. Okay, so let's Come back to the analysis. Okay, so what we are observing about static friction, that is explained over here. That when my external force was, let's say, 0.2 F naught, static friction acting on the block will also exactly be 0.2 F naught. It will adjust itself according to this. By the time I've increased the force from 0.2 to 0.5 F naught, static friction has also adjusted to 0.5 F naught. So it goes on adjusting in such a way that it balances the external force to prevent slipping. But this process of adjustment, it cannot happen, for unlimited amount of force. There's only a certain limit up to which it can happen. And that is the upper limit or the maximum limit of static friction. In this particular example, we have taken it as the constant F naught. We'll understand it with a numerical example also, but here we are just conceptually understanding it. So for any value of force less than F naught, external force less than F naught, what is happening? My static friction is balancing the external force. It is adjusting itself according to external force. But the moment my external force exceeds that limit F naught, the static friction cannot do this process. It cannot adjust accordingly. Okay, so there is a special name that we give to this upper limit, and that is called limiting friction. Yeah, so if F is equal to F naught, we saw, na, it is balancing. F naught तक तो acceleration नहीं हो रहा है ना बेटा. Up to F naught, there is no balancing. I mean, there is no acceleration. There is no slipping. We saw that for F less than equal to F naught. So this includes equal to. Acceleration is 0. And static friction is equal to F. Okay. But the moment F becomes greater than F naught, the block starts accelerating. So kinetic friction takes over. Because slipping has started. Okay. So anyway, let's come back to static friction. So this maximum limit of static friction, or you can say this is the maximum possible value maximum possible magnitude of static friction. This is given a special name. It is called limiting friction. Okay. And we will see that this limiting friction, it depends on two things. The normal reaction at the surface of contact, N. And it also depends the materials of the surface of contact. Okay. So for example, okay, wooden block on concrete surface will have more friction than the same wooden block on a polished marble surface. Okay. Or a stone block on concrete, because it depends on the nature or the material of both the surfaces, the block surface as well as the ground on which the body is lying, both the surfaces of contact. It depends on the materials of both of them. So we have a formula for this, and that shows how it depends on these things. So the maximum static friction available, which is called the limiting friction, is given by a formula μs into normal reaction. Where μs is called coefficient of static friction. Okay. So this is the factor that depends on the materials of the surfaces. Okay, so this coefficient, it is a dimensionless or unitless coefficient, because n here is normal reaction. Okay, so it already has the dimension of force. Yeah, this symbol is called mu. This is the Greek alphabet or symbol, okay, called mu. Okay, and n, I've already told you what it is. N is the normal reaction. Is n is normal reaction force. Yes, they just write down this right now. I'll explain this later again. Okay? We'll understand how different surfaces have different coefficient of friction. Okay. Now the other thing we'll observe in the same above example is that when F becomes greater than F naught, the kinetic friction that acts on the block Fk. Okay. So we are applying the external force F. So kinetic friction is acting on it, and the block is having an acceleration A. Okay, so F minus kinetic friction will be equal to ma. So this kinetic friction that acts on the block will be such that it is a fixed value, okay, independent of F. Okay, and that fixed value of kinetic friction is given by a formula mu k into n, where mu k is equal to coefficient of kinetic friction, okay, and n is normal reaction, okay. And generally mu k is slightly less than mu s. Okay, so the value of kinetic friction is generally slightly less than the maximum value of static friction. Okay, in certain cases, coefficient of kinetic friction can be equal to coefficient of static friction also. But generally speaking, it is slightly less than the coefficient of static friction. Okay, so the difference is that static friction adjusts according to the external force. Okay, the maximum static friction, which is mu s into n, was equal to F naught. Okay, but if the external force is only 0.2 F naught, then the static friction acting will not be mu s into n. It will be 0.2 F naught, which will be a lot less than the maximum value. Okay, if F is equal to 0.98 F naught, then static friction acting will also be 0.98 F naught, which is still less than mu s into n. But the moment F hits the value F naught, the static friction becomes equal to F naught, which becomes equal to the maximum value. So this is the maximum limit. Okay, and therefore, if F becomes greater than F naught, slipping starts. Okay. However, when we talk about kinetic friction, Fk does not adjust in value according to the external force F. Okay. Kinetic friction has a fixed magnitude of mu k into n. Okay. The moment slipping starts. The moment the slipping starts between the block and the surface, a fixed magnitude of kinetic friction acts. So as we increase the external force F, there's going to be no change in the value of kinetic friction. The value of kinetic friction is going to remain fixed. But mu s depends on the material of the body. The maximum limit of static friction depends on my above example, the body was made of wood and I replace it with a body made of some other material like rubber or something of the same weight, we will get a different limiting value of static friction. You understanding, Diti? The maximum friction available to us, that depends on the nature of the body also, not just the normal reaction. Yeah. So you can compare two bodies of the same weight, which are therefore having the same normal reaction, but made of different materials. So the maximum limit up to which we are applying, yeah, I explained that, Kunal. You've written that above already. Mu depends on the nature or the material of the two surfaces in contact. We've already written that point above. So just write down this section now so that we can understand this better with a numerical example. Mu k also depends on the material. Okay. Coefficient of friction also depends on material. This, like static friction coefficient, this also depends on the materials of the two surfaces. Does not depend on external force or any other factor. It just depends on the surfaces of contact. Yeah, let's come back to this. So as I was saying, suppose the values given to us are like this. Now the mass of the block is suppose 10 kg and G is 10 meters per second square. Okay. And we are applying that type of force that was gradually increasing with time. Okay. So our force is increasing with time. Okay. So if the block starts to accelerate when F is greater than F naught, find first of all F naught. What is the value of F naught? Okay. Secondly, find the friction. Okay, whether it is static or kinetic. When F is equal to 30 newtons, F is equal to 40 newtons, F is equal to 60 newtons, and F is equal to 80 newtons. Okay. And find the acceleration of the block, okay, if any, when F is equal to 30 newtons, F is equal to 60 newtons, F is equal to 80 newtons. Okay. So let us work this out numerically. So these things are given to us. The coefficient of static friction, the coefficient of kinetic friction, the mass of the block, and the acceleration due to gravity. And F is again a horizontal external force. Okay. Gradually increasing with time. Okay, so anybody got the first part's answer? What is this maximum value of force before slipping starts? Yes, that's correct, Yash. Very good. That's correct. Anyone else got the answer for F naught, the first part? Yes, Kunal correct, Vashist correct, Diti correct, very good. Okay, so as you can see, it's just a numerical application of the concept we've just discussed. Yes, Shweta correct, very good. So you can see that for F less than equal to F naught, the acceleration of the block is 0. So what is happening? Static friction is balancing F. But also the normal reaction is equal to the weight. So we have normal reaction equal to mg. So from that we understand the normal reaction is 100 newtons. Okay, and for this condition, we have static friction is equal to F. Okay, now maximum static friction is therefore equal to F naught. Okay, so that maximum static friction is given by this. So that is 0.42 into 100 newtons. So that means that the value of F naught, which is equal to the maximum or the limiting friction, will be 42 newtons. Okay. So in language, we say that this is the limiting friction available. This is the limiting friction or maximum available static. And that one's value is equal to F naught, and that's 42 newtons. Yes, very good. Yes, that's correct. Okay. So in this case, you can see that F is less than F naught. So acceleration will be 0. Okay. And static friction will be equal to F. So in this case, a static friction of 30 newtons will be acting on the block. Same for this. A static friction of 40 newtons will be acting. Okay. But now in this case, what is happening? In this case, F is greater than F naught. So slipping is taking place. Okay. So that will be a different situation. The friction acting will be kinetic friction, and that will be mu k into n. So this type of friction will be acting, and when we see that will be also be 40 newtons in magnitude. So let's understand this here. For second C part, when F is greater than F naught, okay, kinetic friction of mu k into n acts, okay, and the acceleration is non-zero. So at that point of time, this is what happens. Kinetic friction of mu k into n acts, okay, and F minus kinetic friction is equal to ma. So this has a value of 0.4 multiplied by 100. So 40 newtons. So the kinetic friction, the moment slipping starts, kinetic friction of this much will be acting, 40 newtons. It doesn't matter whether the external force is 60 newtons or the external force is 80 newtons. There will be a kinetic friction of 40 newtons only acting. Whereas until slipping was occurring, the static friction was adjusting itself according to Yes, very good. Yes, that's correct. So therefore, you can see over here very easily that this acceleration is 0 because there is static friction. Okay, but this acceleration you can see will become F minus kinetic friction upon mass. Okay. So 2 meters per second square. In this case, the acceleration will have increased to 4 meters per second square. N is not a factor of F naught, beta. F naught तो limiting friction का value है ना. So limiting friction the coefficient of static friction into normal reaction. So coefficient of static friction was given to us in the problem, Kunal, as 0.42, and the normal reaction equals the weight that you can see from the free body diagram. So F naught is the maximum external force that can act such that there is no slipping. So that is equal to the limiting friction, no? So limiting friction depends on normal reaction. That's how we are getting the value of F naught. It is not a derived formula, but I told you it is an observational fact from experiment. It is the nature of friction. Okay, so hope all the parts are clear. So another thing we can observe now for this will be that now suppose we again compare the graphs of force versus time. Okay, and in this graph we know that at some time t naught, the force is reaching the value of F naught equal to 42 newtons. Okay. Now let us talk about whereas suppose at some time t1, the force is reaching a value of 60 newtons. It's force in newtons. Okay. And at some time t2, it's reaching a value of 80 newtons. So now simultaneously, if we look at the acceleration versus time graph, acceleration in meters per second square, now this time is t naught. Now, in this graph, what we will observe is that right up to T naught, the acceleration is 0 because the force is less than 42 newtons. Okay, but at the instant when the force becomes just greater than 42 newtons, the acceleration doesn't start from 0 because the friction changes from static to kinetic friction. So the friction suddenly drops from its value of 42 newtons to a value of 40 newtons. Okay, so for F equal to F naught, okay, static friction is equal to 42 newtons, which has reached its limiting value. So this is the maximum limit, but the moment F becomes greater than F naught, the friction changes to kinetic friction. So it becomes 40 newtons. Okay, so when F is just greater than, slightly greater than 42. Okay, so it's almost equal to 42, but greater than. Okay, then the acceleration will become how much? It will become F minus kinetic friction divided by mass. So this will be almost equal to 42, slightly greater than 42, but the kinetic friction will be 40. So divided by the mass. So the acceleration will start from a value of 0.2 meters per second square. And then by the time you reach the time of T1, when the external force has become 60 newtons, you can see that the acceleration has increased by then to 2 meters per second square, which we had calculated. By the time you reach the time T2, when the external force has become 80 newtons, the acceleration would have increased to 4 meters per second square. Okay, so this is the correlation of these two graphs. Okay, so when this thing is just about greater than 42, the acceleration starts from a non-zero value. It starts from a very small but non-zero value because there is a sudden drop in friction. The static friction was going up to 42 newtons, but the moment the slipping starts, at that instant, the friction suddenly drops from 42 to 40. So it starts with a sudden acceleration of 0.2 meters per second square. It doesn't start with an acceleration tending to 0. Okay, so now let's pick up some more examples. So next, let's see a situation like this. Where what we've done is we've kept two blocks stacked on each other. This is M1, this is M2. Now this is a rough surface. This is a rough surface which has coefficient of static friction, suppose 0.25, but coefficient of kinetic friction 0.24. Okay. Whereas this one is a smooth surface. There's no friction between the two blocks. And initially they are at rest. So initially blocks M1 and M2 are at rest. So given that mass of this block is 4 kg and mass of this block is say 11 kgs. Now we start pushing this with a horizontal force F applied on M2. So now a horizontal force F is applied on M2. Okay. Find the frictional force, okay, whether it is static or kinetic, okay, and accelerations of M1 and M2 if this external force that we are applying is 30 newtons. Okay. Sorry, let's make it even lesser. Actually, 30 newtons is fine. Second case, it is 60 newtons. Take acceleration due to gravity as 10 meters per second square. So the method of solving this will be that you make the free body diagram of the two blocks, okay, and try to understand from the free body diagram what is the limiting friction available to the block M2. And from that you understand that when we apply a force of 30 newtons or 60 newtons, whether or not there will be slipping. Okay, so anybody's worked out how much is the limiting static friction? Yes, Shweta, your answer is correct. Vashisht, no, the answer is not correct. Okay, you have to understand that at the surface of contact between M2 and the ground, how much will be the normal reaction? So the first thing you have to understand here is between M2 and the ground, what is the normal contact force? You'll see that is 150 newtons. Okay, because the vertical forces are like this. Weight of this block is balanced by the normal reaction that the block below it applies on it. So if this normal reaction is N1, you can see N1 is equal to M1G. So that is equal to 40 newtons. Okay. Now on the second block, there are three vertical forces which are acting, not two. There is this N1 acting downwards on it. There is its own weight. Okay. And there is N2. So this normal reaction is balancing the sum of N1 plus M2G. So this normal reaction is becoming 40 plus 110. So this normal reaction is 150 newtons. Okay. So when we apply this external force, okay, if it is comparatively less, then friction will be able to handle it, because static friction will be successful to prevent slipping by balancing this. Okay. So you can see that, let's not write this as static friction yet. So you'll see that if F is less than equal to the maximum static friction, then static friction will balance F and acceleration will be 0. Whereas if this force is greater than the limiting friction, the block M2, okay, then M2 block will slip forward with acceleration non-zero, and the friction will be kinetic friction. 37.5 बेटा, 3750 कहाँ से आया आपका? Okay. So now you can see that this static friction's maximum value is going to be what? It is the coefficient of static friction into the normal reaction with the ground. So that is 0.25 into 150. So that's 1/4 of 150. So that is 37.5 newtons. Okay. So that is the conclusion now. Therefore, for F less than equal to 37.5 newtons, okay, acceleration will be 0 and F will be balanced by static friction. Whereas for F greater than 37.5 newtons, a kinetic friction of mu k into n will act, okay, which is 0.22 multiplied with 150. So 0.24, my mistake. Yeah, 0.24 into normal reaction. So that is 150. Okay. So that will become how much now? Little bit less. It will become 36 newtons will act. Okay, and M2 will have an acceleration of F minus kinetic friction divided by its mass. So for the first case, F is equal to 30 newtons. There is no slipping. Okay, so this block also remains at rest. This block also remains at rest. And this force that we are applying of 30 newtons is balanced with static friction of 30 newtons. Okay, so acceleration will be 0 and static friction of 30 newtons will act. But in the second case, there will be slipping. Yes, that's correct. So for the second case, we'll have to apply this situation now. This one, because F is greater than 37.5. Okay, now let's come to the second case. So in the second situation, what is happening is that we are applying a force of 60 newtons. So slipping occurs. But just because slipping occurs doesn't mean that the upper block will move. Initially, the upper block will remain where it is because there's no horizontal force acting on that block. Then, of course, it will fall off. So that's a different matter then. But I'm just talking about initially when we are applying this force, just at that instant, when this force is 60 newtons, there will be kinetic friction of mu k into n, which we saw is 36 newtons, which acts on this. So this block starts sliding. Whereas this block momentarily remains at rest, then it of course falls off. So basically what will happen is that, you are applying this force on this. So this starts moving like this. And then after a while, this happens. And then, okay, If you continue applying the force, that is, this happens and then it topples over, falls off like this from here. But anyway, we are just talking about this initial instant. So at this instant, what is happening? The upper block is at rest. This is moving. Okay. And of course, vertical forces you've already seen. So I'm not too concerned about that here. These vertical forces are there. Okay. But main thing we are concerned about is the acceleration. So for M1, it's at rest. For the block M2, we'll have F minus kinetic friction is mass into acceleration. But whose mass? Only M2, not the whole system's mass. So 60 minus 36 should be equal to 11E. Okay. So acceleration will become 24 by 11. Okay. Or approximately approximately 2.2 meters per second. So hope the concept is clear. Okay, very good. So we will conclude the session here today, people. Next time we will pick up things like friction on an inclined surface and things like that. But basically, once you're clear with the concept of limiting friction and the situation where slipping is occurring versus the slipping where the situation where slipping is not occurring, or static friction is able to prevent slipping, you should be able to handle any problem with friction. Just a matter of making the correct free body diagrams. So you can start going through some solved examples from H.C. Verma. Yeah, we'll do the spring force problems. No, you can already start doing the spring force problems. There are 2 or 3 of them in the H.C. Verma Newton's laws exercise. In spring force problems, you just apply the spring force concept we discussed in the last lecture. Just like you have tension in a thread, like that, the tension in the spring has to be replaced with Kx. हाँ कुणाल, यहाँ पे M1 का acceleration होगा ही नहीं ना. That is what I'm saying. Initially, when you start applying the force from below, the block M2 is slipping, but M1 remains at rest. It does not move. It's only when M2 moves forward a little bit and then it topples over. Okay, so we're not concerned about that. We're concerned about initially when you're just applying the force. At that point of time, what is the acceleration? So M1 doesn't have any acceleration. It just remains at rest. Is it clear? Okay, good. Right, so you can start working on some examples from H.C. Verma friction chapter. You can also read ahead about or read the chapter of friction from Resnick Halliday, and similarly continue ahead with problems from friction from H.C. Verma. So that's it for today's class, people. Wish you all the best.